Hi, I'm Felipe Monteiro, and I'm going to talk about model checking C++ programs. This is a partnership with Mikhail Gadelha and Lucas Cordeiro. We are from Federal University of Amazonas, Gadelha Institute and University of Manchester. Let's jump into the motivation for this work. Security is for sure one of the major concerns for any developers working across many applications this day. And here is an interesting piece of data that Microsoft shared back in 2019. They evaluated all the security patches from the past 12 years, and they realized that over 70% of all patches have the same source of vulnerability. Those were memory corruption bugs into their C and C++ code. The more they were adopting open source software and increasing the code base, the problem was just getting worse. So how can we make sure the developer have tools in their hands that they could use to ensure that those systems free of those memory corruption bugs? Many companies these days are now investing into formal automated reasoning formal techniques across all parts of their business. And here's a quote from Byron Cook highlighting how AWS is using automated reasoning techniques for to increase the confidence, both functional and security of their systems. Here's another piece from Peter O'Hara back in Facebook Research, where he highlights that there has been a tremendous increase in research, in valuable research in formal methods, but we still need to bring it up and bring those research to industrial code bases. And this is happening more and more these days, but it's an interesting call out to build tools to hand to developers so they can get benefit from all of this research. And here's how we come to our research questions. How can we apply these formal techniques to ensure the memory safety, to ensure memory safety of software written in C++? We are targeting memory safety now because this kind of vulnerability is at the core of managed security issues. And we are targeting C++ because if you take a look, for example, at SVComp, there are many initiatives targeting C, but very few that actually try to tackle the very complex features that C++ provide. We wanted to invest in software model checking, targeting specifically C++ to try to solve that problem. And we are using ESBMC as a way to implement those ideas. Well, so what are the major contributions of this work? First of all, we describe our experience by tackling important features of C++, for example, template instantiation, arithmetic, and polymorphism, and how we build our type checking engine to deal with those problems. The second one is that C++ provides a very rich set of libraries called STL, Standard Template Libraries. And we developed a set of operational models that extract those libraries from the verification, but also include additional checks to see if the program under verification is using the library correctly, and it wouldn't lead to any undefined behavior or memory safety violations. We explain all of the throw and catch except rules that are supported in SPMC, and that includes terminate and unexpected handlers. And at the end, we evaluate all of our technique implemented in SBMC using a very large set of publicly available C++ benchmarks. We have over 1,500 benchmarks that are designed to try many libraries from the STL and many features that C++ provides. And this is our set of contributions. So let's get to our background theory. I'm not going to go into too much details, assuming the audience will know more about this, but I think it is important to tackle about the general idea behind the SPMC, which is about a model checking tool. So we represented the program as a transition system. We are going to unroll this transition system up to about K. And here I'm talking about, for example, loops in mind. We are going to check our property in every state of that system, encode everything into a verification condition, and then use SMT to try to solve that formula and see if we could get a counterexample that highlights a bug at a particular state. This technique has been used for the past 20 years in embedded software. ESBMC is open source and it's targeted not only C++, but also C programs, single and multi-threaded. At this work, we do not focus on multi-threaded C++ programs. It's a partnership among all of the universes that you see on your screen. It does not require the user to provide any annotations in the program, although the user could enrich the verification by adding assertions to your code. And it converts everything using SMT, using background theories and solves with SMT solver. We have quite a few SMT solver support in our backend. This is the architecture of ESBMC. For C programs, we use it for front-end Clang to generate an AST. And here I wanted to highlight, we do not use LLVM. We use Clang to generate a reliable abstract syntax tree and use that for verification. For C++, on the other hand, alongside with the program verification, the operational model, which is the set of instructions for the STL, we have our own parser that is heavily based on the GNU C++ compiler. And at this stage, we use our own type checking engine to deal with template instantiation, inheritance, and so on. We then convert the program to a go-to representation. Is a program designed specifically for verification, which basically contains assignments, conditional and unconditional branches, assumes and assertions. We deliver that to our symbolic execution engine, which will derive all of the safety properties. We encode that into our verification conditions and use a set of SMT solvers in our backend. We actually have 6 now. We just added a new one. We also perform an evaluation on the SMT solvers, and for our experiments, we mostly use Bulector because it seems more efficient for this type of application. If the formula is set, we get a counterexample highlighting the bug. Otherwise, the verification looks successful. Now that we have in mind the architecture behind ESBMC, what is it specifically about C++? Let's start with the properties. So of course, we want to be able to handle all memory safety properties that ESBMC already provides. For example, null pointer dereference, pointer arithmetic overflows, and so on. We also extend ESBMC to treat other OOP properties, for example, multiple inheritance and polymorphisms in this scope resolution operator, and any errors that might occur using those features. We extended encoding in our operational model specific properties of STL that we injected during verification. For example, if the program is using correctly STL containers. And at the end, we also have our exception handling support. And here I highlighted that we extended for terminating unexpected handles as well. To provide a way to check for all of those properties, we needed to cover major features of the C++ language may offer. But let's see ESBMC in action with a real example. Here a very simple C++ program, which contains a bug right here. At the very beginning, we have a plate function, which is gonna scan a particular, some sort of container, and then replace one value with a new one. And here we have a use case of this function, where we created this array, we created a vector, and then we replaced 20s by 99 in the vector. You can see in the comments the values, and we make a couple of assertions and print out the result. Here, there is a particular bug. Let's check this with ESBMC. To check that program with ESBMC, we can invoke our tool, pass the program. We know that we have loops in our program, so we needed to provide a row. Our array is up to size 8, so we wanted to provide an unwind that can cover, that make sure that this entire loop would be unwind. And we needed to pass a path to our standard libraries right here. If we invoke ESBMC into this program, we get a counterexample and a problem, and the error message says undefined behavior request positions out of range. If we take a look at the problem at the program again, we will see that here we were trying to access the 8th position of our array, but it only goes up to 7. This is undefined behavior by the standard library. If we fix this and we run with ESBMC, we will get verification successful. And this is a small example of how we were combining the support for templates, our operational models right here to check for particular properties in our C++ code. So now let's get back to our presentation. Now that we've seen ESBMC in action, what is the experimental evaluation here? So we wanted to answer basically 2 questions. The first one is how accurate ESBMC was, and the second one is how it performs, again, state-of-the-art model checkers. Well, we got together this extensive set of regression tests that covers of standard gainers, features from inherent polymorphism, exception handling examples, and many other C++ 2003 features. We evaluated against LLVMC and Divine. LLVMC is also an SMT-based bounded model checking tool that uses LLVM, and Divine is explicit state bounded model checker. And we use this configuration for our experiments. We were able to see that ESBMC successfully verify approximately 85% of the entire benchmark regression suite in approximately 4 hours, outperforming both LLVMC and Divine. LLVMC also had a huge verification time, over 14 hours. If we take a closer look at the results, you see that ESBMC outperformed in every single category: C++, containers, inheritance, polymorphism, and exception handling. We do not count LLVMC for exception handling because the tool does not have support for it. So running all of the others benchmarks, we make sure they do not contain anything related to exception handling. We also compare the memory consumption and the time consumption and the verification time for each tool. ESBMC is the tool that consumes the most memory. This is related to our generating SSA forms from the program, but we were working on an optimization that will decrease significantly the use of memory throughout the verification. And we also apply ESBMC on a real-world application. It was provided by Nokia Institute in Brazil. The Sniper application is responsible for monitoring traffic conditions on a network using this particular protocol, M3UA. The Sniper application contains over 2,800 lines of code, 85 methods, but we are only able to verify 50 methods due to confidentiality issues. So the remaining methods were not provided to us. ESBMC was able to detect 5 errors. LLVMC was able to detect 3. Divine couldn't handle in the application because it didn't have support for all the libraries used in the application, and all bugs were confirmed by developers. So what are the conclusions here? We implemented this approach to handle C++ programs using SMT-based bounded model checking in ESBMC, and we got a successful rate of up to 85% in 4 hours. This is a push-button approach because we do not need to provide any annotation to the program. We do observe that ESBMC using more than the other verifiers. So this is one of the points that we still need to work on. For feature works, one of the lessons learned is that using our own front end can be very heavy, so we wanted to switch to Clang. And this is a major engineering effort, but it will provide us with a lot of benefits. For example, Clang would be able to catch errors in template instantiation without us having to worry about this. We wanted to focus only on the verification side, which is the encoding to SMT. We have more details on that in our paper. But this will set a very strong foundation for C++ support in CBMC. Download this today, and I hope you have enjoyed the presentation. Thank you very much. I will take any questions. Bye.